How are y'all today?
How are you?
Good. Not bad for Tuesday, right? So I'll pass your exams back at the end of class, and hopefully we'll have time so you can look over and ask questions if need be. The key is posted and the blank exam is posted, so make sure you're looking over like what you missed, comparing that to the key, seeing why you missed something is important. That way you know what to focus on, especially because some of this material will show up on the final again. So then today we're starting sequences and series. And so chapter 10 is, we start off with an overview of both. So 10.1 deals with both sequences and series. It's just a little bit about each one. We'll look at sequences in 10.2, and then the rest of the section, or the rest of the chapter, is devoted to series. So the idea of what we're like building up to is the goal of looking at sequences, in particular series, is so that if we look at an integral like e to the x squared, and we need to be a little more specific, a definite integral from like 0 to 1, let's say. This is actually something that came up on the exam too. The idea is that e to the x squared does not have a known antiderivative. There are many functions that don't have known antiderivatives. So we can't just say the antiderivative of e to the x squared is this function of x and plug in the bounds. So the problem with that is, I guess maybe when you look at the function, from like 0 to 1, or even this function, like we had on our exam, neither one of those have a known antiderivative, but clearly there is an area under the curve, right? So then how do we deal with those types of things? And the way we deal with those types of things is expressing them as a series, as opposed to working with the function itself. So our goal here is to ultimately build up to looking at certain types of functions that don't have antiderivatives, and instead look at the integral from 0 to 1 on what we'll say is, for now, is just an infinite polynomial. So in other words, we come up with this infinite polynomial that is equal to e to the x squared, and then we just integrate term by term instead of working with a function that doesn't have an antiderivative. So then, the question that comes up maybe is like, well, how could I guarantee that this is accurate, right? Like, how many terms of that polynomial do I have to look at to make sure that I'm getting a really accurate representation of the area? And we'll talk about that when we get there, but it's really based on sort of like a user-specified accuracy, right? Like if in the engineering field, they'll say like, hey, machinist, machine this part to like 0.01 plus or minus 0.01, right? And that's your tolerance. So it's really just specified. It says, find this antiderivative, or find this definite integral, and maybe we want you to be within 10 to the negative 5 worth of accuracy. So then the more accurate you have to be with these types of infinite polynomials, the more terms you need to look at is basically the gist. But that's, other functions too, but that's what we're kind of building up to. And really the general idea is what functions, if and when we can, represent them as an infinite series. That's just an infinite sum. Because some functions, as we'll see, we can represent as basically a polynomial. So that's kind of the idea in general. So then, working backwards here in chapter 11, it really builds up to what we call Taylor's theorem. And I don't know, do any of y'all remember doing linear approximations in Calc 1? Yeah. So what did the linear approximation do for us again? It approximated something linearly. Yeah, exactly. That's all it did. You have some like complex function that's maybe like super curvy, right? And then you instead of looking at the function, you said, well, what's the tangent line at this point? And let me use the tangent line to approximate function values, right? So that's all the linear approximation was. So think of Taylor's theorem as so think linear approximation. Linear, but much better. The bulk of chapter 10 deals with series, which are infinite sums. And particularly with series, what we want to know is there a way for us to determine if I add up an infinite number of things, does it actually approach a finite number? In other words, we're asking, given this particular infinite sum, does it converge or does it diverge? So those are most of the tools we develop are in context of testing a series for convergence or divergence. Okay. So the idea there is if we can guarantee a series, an infinite sum converges to a finite number, then in chapter 11, what we're going to do is we're going to put a function in with that series and then guarantee that that series converges to not a number, but a function of x. So we look at numbers first in chapter 10, and then we modify that with functions in chapter 11. And before we do all of that, we look at sequences. And sequences are we'll just think about them as a list of numbers. We're not doing anything to the numbers other than just listing them. So that's kind of the overview of chapter 10 and 11. Chapter 10 and 11 are closely related. And then, so when we define a sequence, we'll see this notation here, this a sub n from 1 to infinity. The n is just the index, like in the sum. And the index is it's advanced, like the index n is just counting numbers, 1, 2, 0, 1, 2, 3, 4, 5, 6, so forth. Sometimes starts at 0, sometimes starts at 1. And so if we see this a sub n from 1 to infinity, all that means is just list out these numbers that are determined by a sub n. So a sub n, we'll see, can be defined in a couple of different ways, but the idea is it gives you a sub 1, a sub 2, a sub 3, a sub n plus 1, and so forth. Where each one of those a sub n's would represent a number, or would be a number. So the kind of the terminology here, like this a sub 1, we would call that the first term, or the initial. And like this a sub n, we just say that's the nth term. So it is like this discrete thing. It's not, we're used to working with like continuous values of x. Now we're sort of stepping back into this discrete world where it's, it's just consists of numbers. Or if you think about it in space, it would just be, points. The points aren't connected because it's not a continuous thing. So the patterns or the ways we can write this particular a sub n are two. We could write them recursively or we could write them explicitly. And what we mean by explicit, hopefully that makes sense, as we've seen like functions defined explicitly in terms of x. So like an explicit formula just tells you, we'll just write this out. What it tells you is if you have n, like n equals 1 or 12 or whatever, if you have n, then you can obtain the nth term. So for example, a sequence defined explicitly, we could say like a sub n is equal to 2 times n. And here we'll say n is 1, 2, 3, etc. So that's an example of an explicitly defined sequence. And then a recursive formula is where the next term or terms depend on the previous term or terms. So the next term depends on the previous term or terms. Example of that would be a sub n is 2 times a sub n minus 1, where a sub 1 is equal to 3. That's it. I don't want it to look like a J. So recursively, we see that the nth term is just twice the nth minus 1 term, or the next term is twice the previous term. See? That's not defined explicitly. Explicitly means like I can tell you, hey, what is the 100th term, and you can immediately tell me what the 100th term is. With a recursive formula, since each successive term is built off the previous term, to know the 100th term, you need to know the 99th. And to know the 99th, you need to know the 98th, and so forth. So those are the two ways, and that's just one example, of course, but those are the two ways that we see sequences defined. So let's just work with these two examples and say, if a sub n is 2 times a sub n minus 1, the first term is 3. Let's come up with let's list some of the terms here anyways. What would a sub 2 be? 6, because a sub 2 is actually just 2 times a sub 1, which is 2 times 3. Okay. A sub 3 then is twice the previous. So 2 times a sub 2, which is 2 times 6. And however many terms we wanted, we could get. We just have to slowly increment this. So a sub 4 is twice the previous, and so forth. Let's just list one more. So the thing with both of these forms is typically if I can express a sequence as a recursion formula, I can also express it explicitly. Or if I can express explicitly, I can also come up with a recursion formula. And really those things aren't unique, because I bet there's, we could all look at this sequence 3, 6, 12, 24, 48 and come up with a different way to obtain those numbers. So they're not unique representations, but we can go from one form to the other. Okay. So let's also ask then for a sub n equals 2 times a sub n minus 1. Can we come up with an explicit formula? So we can sit here and just try to figure out the pattern, or I'll just write one out. So we can explicitly define whatever term, the nth term, as 3 times 2 to the power of n minus 1. So you can verify, does that actually work? What would the first term be according to our explicit formula? Yeah, so this is 3 times 2 to the 0. A sub 2 would be 3 times 2 to the first, which is 6. A sub 3 should be 3 times 2 squared. 3 times 4 is 12. A sub 5 should be 3 times 2 to the fourth, which is 48. So you could verify that that actually works. And maybe you could come up with another explicit formula. But that's the idea. We can go back and forth between representations. Anybody have any questions about that?
Did you just guess? Or did you take the A sub 1 term and then multiply it?
Well, yeah, so here, the idea was, we're looking at twice the previous. So if we kind of wrote that out sort of the long way, let's do this here, if I can fit this underneath. So we had the second term was 2 times 3. The third term was 2 times 6, but that's 2 times 2 times 3, right? And the fourth term was 2 times 12, so that's 2 times 2 times 2 times 3. So the factors of 2 are 1 less than our index there, and we always just have that multiple of 3.
So just recognizing the pattern.
Yeah.
Which is in the same.
Right, exactly. It's just a pattern recognition when you're converting from one to the other. Now, 8.1 has a little bit of this stuff, and 8.2 is all of this stuff. But honestly, outside of that, we don't do a whole lot with sequences or just lists of numbers. Some of their properties help build up the series stuff, and when we actually start adding these values. I don't know. It's always I feel like sequences almost shouldn't be taught, because they're really not that crucial. And then the properties of sequences get mixed up with properties of series sometimes. And so I don't know. We have to talk about them though. So that's for that one. How about if we look at this explicit formula for like a sub n equals 2n, for n equal 1, 2, 3, etc. Can we come up with an explicit formula for that? So we'll just list out the first 5 terms like we did on this one. A sub 1 is 2 times 1. Let me do this. A sub 1 is 2 times 1, which is 2. sub 2 is 2 times 2, which is 4. A sub 3 is 2 times 3. A sub 4, 2 times 4. And a sub 5, oops, 2 times 5. So we come up with the sequence as 2, 4, 6, 8, 10, and then so on and so forth, right? We keep going, but our sequence is 2, 2, 4, 6, 8, 10, so on and so forth. So that's our list of numbers, our sequence. So for that particular sequence, can we write a recursive formula? For that one, how would we define the next term in terms of the previous or previous terms?
A n minus 1 plus 2.
So say that again. A sub n, like this, is equal to
N minus 1.
n minus 1.
No, this sub n minus 1.
A sub n minus 1. Okay. The previous a sub n minus 1. And what was it? Plus 2. What do y'all think? The next term is the previous term, a sub n minus 1 plus 2. Seems reasonable. With recursive formulas, if you're going to define the next term in terms of the previous, you always have to know what the starting term is, right? Like if you didn't know where this started, like this, there's no way to define that. So we also have to say where the first term is equal to 2. That way we can get the 4, the 6, the 8, and the 10. Otherwise, if the first term was 5, then the next term would be 7, then 9. So the recursive formulas do stipulate where you start. All right. Does anyone have any questions on those? Okay, so then that's kind of the idea with some of these, is it says, here's a sequence, 1, 4, 9, 16. What are the next two terms? Write the sequence with an explicit formula and a recursive formula. So what are the next two terms here? 25 and 36. Okay. So as far as the explicit formula, and again here, just make it simple. The index starts at 1, and then it's 2, then it's 3, etc. So what would the explicit formula for that be? In other words, the nth term is obtained how? Squaring whatever your n is. Okay. How about a recursive formula for that sequence?
an equals an minus 1, that underneath the square root, plus 1,
Plus 1,
and then all of that squared.
and all of that squared, like that.
A1 equals 1.
And the first term is 1. What do y'all think? Does that work? So you could just check, right? We could say, all right, well, the first term is 1, then according to our definition, what does a sub 2 equal? A sub 2 is the square root of the previous term plus 1, and then we're going to square that quantity. In other words, we have the square root of 1 plus 1 squared, which gives us 4. And again, just because it works for that one doesn't mean it works for all of them, but if you check a few and you're confident that you know those things are coming out right, it's probably a good sign. And there's really no way you could check all of the terms, right? Okay, so maybe let's do another one. A sub 3 would be then the square root of A sub 2 plus 1 all squared. A sub 2 we just said was 4, so we have the square root of 4 plus 1 squared. So we have 2 plus 1 squared, which is 9. So far we have 1, 4, 9. Seems to be working. Yeah, maybe you can think of another one. But the idea is once we have one of those recursive definitions, it's really not a unique thing. We could also say, we could say that the next term, the a sub n plus 1 term, is equal to the square root of the previous a sub n plus 1 squared. So that could work as well. It's the same statement that we started with. All we did was shift these indices. I added 1 here, so I add 1 here, and that gives me that and that. So it's really not a unique thing in that sense. Generally speaking, it is, but so it's pattern recognition. If you're good at that, this should come easy. If not, you might have to think a little bit and just try stuff. Really no other way around it. Okay. Any questions on that? So find the first 5 terms of the sequence 2 to the n over n factorial from 1 to infinity. We're only going to find the first 5 terms. Does everyone remember the factorial? The n exclamation mark? N factorial? No? Yes. So let's write that out in a minute and give some examples. For example, if I write 5 factorial, what I mean is 5 times 4 times 3 times 2 times 1. So it's like this shorthand for like this discrete product, if you will. 3 factorial is 3 times 2 times 1. So n factorial is just n times n minus 1 times n minus 2 times all the way till we get to 1. I mean, really you just need to stop at 2, but that's how it's defined. Oh, also, this is where, to confuse things, but where 0 factorial is defined as 1. This is something that came up as like a probability thing. So it's very heavily represented in counting problems. Have y'all heard like permutations and combinations and probability? So that's where it shows up a lot, but I mean, it's just all over the place in probability. Fortunately, we don't do any of that because it's stuff's a pain. All right, so our sequence, 2 to the n over n factorial. First 5 terms. So a sub 1 is 2 to the first over 1 factorial, or 1 times 1. So we end up with 2. And so forth. A sub 2 is 2 squared over 2 factorial. So we have 4 over 2 times 1. A sub 3 is 2 cubed over 3 factorial, which is 8 divided by 3 times 2 times 1. 8 over 6. 4 over 3. I said the first 5 terms. Okay. Go over here, a sub 4 and a sub 5. Alright. So 2 to the 4th over 4 factorial. Is this our 4th term? So we have 16 over 4 factorial would give us 24. And, you know, we could reduce this later, but then our 5th term, 2 to the 5th over 5 factorial. 32 over 5 times 4 times 3 times 2 times 1. 5 factorial. Just write this out. Notice also the pattern of the factorial, right? Like if I say it's 5 times 4 times 3 times 2 times 1, isn't this stuff right here 4 factorial? So 5 factorial is 5 times 4 factorial, which, you know, it may seem like, you know, why would we want to look at it right this way? Now it doesn't really benefit us to look at it like that, but as we move into series, it's really beneficial to be able to like break down a factorial. So it's worthwhile to think of it as 5 times 4 factorial, or we could even say that's 5 times 4 times 3 factorial, right? And so forth. So it is beneficial to think of it that way when we start doing particular things with adding these values up. Okay, whatever, reduce that if we need to, but that's the idea. The sequences that are defined explicitly, even if we want to define the 100th term of that sequence, all we do is plug in 100 for n and we have the 100th term, right? So those primarily we deal with sequences that are defined explicitly. And the next term, the first 5 terms of the sequence, cosine of n pi. So the first 5 terms of that. I should have left some more space. What would our first term, a sub 1, be? Yeah, it's the cosine of 1 times pi, or the cosine of pi. Cosine of pi gives us
-1.
-1. A sub 2 is the cosine of 2 pi, which gives us
Just 1.
+1. A sub 3, cosine of 3 pi, which would give us
-1.
-1. A sub 4, cosine 4 pi, which is 1, and then a sub 5, cosine of 5 pi. So you see, if we were to write out all the terms of that sequence, it's just -1, 1, -1, 1, right? So you just have this forever as the sequence. So it's alternating. We call that an alternating sequence because the signs are positive then negative or negative then positive. Okay. So we do end up talking about those. They kind of have their own specific section when we start adding the terms up. Another way we could see an alternation of sign is with this -1 to the n, or like -1 to the n plus 1, stuff like that. So this also gives it's a switch from negative to positive. It gives us the alternating signs. So that's all that contribution, -1 to a certain power. It's either -1 or +1. It's all it ever contributes to a series or a sequence. So here we have a sub 1 is -1 to the 1 times 1, which is -1. A sub 2 is -1 squared times 2. So that gives us a +2. What would the next term be? -3, the next term, +4, the next term, -5. Let's see how that works. A sub 3 is -1 cubed times 3. So after seeing how that operates, we could notice how this pattern continues on. A sub 6 is +6, and so forth. So that -1 to a power only contributes to the sign. Right at this sequence here. That would be our sequence. So, like, if we were to look at a couple of these sequences that we wrote out, well, we didn't actually write that one out. But like, if I asked you, does the sequence -1, 1, -1, 1, -1, etc., does that converge or diverge, or does that even make sense to ask? Could we say that converges or diverges? Would that make sense? I mean, just one more example. We've got 2 there, but I don't know, maybe if we had like 1/10, 1/100, 1/1000, so forth, like subsequent powers of 10. Would it make sense to say, does that list of numbers, if we continued on forever, does it converge to something?
Yeah.
Yeah, we would say it does. Each term is getting smaller and smaller. We could say something like that converges to 0. So, I mean, does that make sense just intuitively, that we can say, hey, this list of numbers actually gets closer and closer to a particular number? How about this one we wrote down here, -1, 2, -3, 4? What would you say about that?
Diverges?
Yeah, it diverges. Does it ever get close to a number? It just keeps getting larger and larger. Sure, we have a positive and a negative, but just think about the positive, like the x-axis, if you will. The positive, then it's negative, then it's positive, then it's negative, right? So it alternates. It's on top than on bottom. But the fact of the matter is the numbers keep getting larger and larger. This one's a little bit, maybe not, but something like this, we wouldn't say it converges either, would we? It doesn't approach a specific number. It really depends on where you're at. Like if you're at the 1,000th term versus the 1,001st term, you've got two completely different things. So this just alternates between 1 and -1, just like a sine or cosine function would. So that one wouldn't converge, but the idea is that we can assign that terminology to a list of numbers. So the limit of a sequence, and we say suppose we've got a sequence a sub n, if it approaches a unique number as n increases, and what we mean by n increases is that we're looking at the limit as n approaches infinity on that particular sequence. If that limit exists, then we have a convergent sequence. We say it converges to whatever that number L is. If the terms of the sequence do not approach a single number as n increases, then we say that sequence diverges. Excuse me. So notice what we're saying here is it's really straightforward. In order to determine if a list of numbers converges, all we need to do is compute the limit as n approaches infinity on that sequence and how it's defined. So for instance, we've got the sequence 1 over n plus 1. We want to know, does it appear to converge? Make a conjecture about the limit, or if the sequence diverges, explain why. So honestly, writing out the first 5 terms or the first 20 terms is really not necessary to determine, does this thing converge? If so, what does it converge to? But nonetheless, the first term, a sub 1, is 1 over 1 plus 1. The second term is 1 over 2 plus 1. Third term, so forth. Fourth term, 1 over 5. And the fifth term, 1 over 6. So let's write it out here. Sequence is a half, a third, a fourth, a fifth, sixth, and so forth. All right, so then looking at that list of numbers, does the sequence appear to converge? And if so, what does it converge to? Converges to 0. What do y'all think? Does that seem reasonable?
Yeah.
How do we know for sure?
1 over infinitely larger number, 0.
Right, exactly. Yep. So that's all we have to look at. What is the limit as n approaches infinity on our sequence? 1 over n. 1 over n plus 1. So the numbers as we progress get smaller and smaller. Remember, it's not that we actually, in theory, it's not that you actually ever reach 0. It's just saying that as n gets larger and larger, the term that we're looking at is smaller and smaller. That's all that means. So as you can see, like, limits at infinity are really a crucial part of both sequences and series. It's primarily what makes the information that we're interested in. It's what makes all of that stuff up, is limits at infinity. So you might need to review limits at infinity because when we compute these things, you might remember as well, like L'Hopital's rule is pretty prevalent with a lot of these. So all of that stuff sort of comes back here in these two sections, or chapters rather. Okay, so we've got to write the first 5 terms of the sequence -1 to the n plus 1 from 1 to infinity, and do the same thing. Does it converge or diverge? All right, so what is a sub 1? And a sub 2? -1, a sub 3? Okay, and a sub 4, and a sub 5. So our sequence, we'll just write it out officially. 1, -1, 1, -1. Oops. Okay. Converge, diverge. Diverges. The sequence does not approach a specific number. It diverges, or it says if it diverges, explain why. Our explanation is it's either 1 or -1. And that's, however much we want to say, but it's not one specific finite number.
Did you say it was oscillate or just
Yeah, we'll eventually look at varying terminology, but yeah, it does oscillate. So in other words, if we were asked to compute what is the limit as n approaches infinity on -1 to the n plus 1, the best we can do is say that it's equal to 1 or -1. That's it. And really, it's a +1 if you're at an even index, and -1 for an odd index. But we generally don't write that anyways because it diverges, so just see it kind of explicitly there. All right, do y'all have any questions so far? That limit process is we'll see we can modify it too, like these recursive formulas, but it's really for the explicit case. Like if I know explicitly how the sequence is defined, if it's defined recursively, we can still work around and look at the limit at infinity, but it's a little bit different. I mean the math behind it's the same, but so we have the sequence. A sub n plus 1 is -3 a sub n, and the first term is 1. So we're going to look at this sequence of numbers and see if it converges or diverges. So a sub 2 is just -3 times the previous term. A sub 3 is -3 times the previous term. So -3 times -3. A sub 4. -3 times 9. -27, and a sub 5. -3 times -27, which is 81. So it's really just kind of like these alternating powers of 3. What would we say about that? Converge or diverge? Diverges. The numbers are just getting larger and larger. Even though it's alternating, I guess we could say diverges. Terms get larger in magnitude or in absolute value, whatever you want to say. So, you know, like for these lists of numbers, it's really straightforward to determine if they converge or diverge. It's basically like if it's a recursive formula or if it's defined explicitly, it's just a limit at infinity. It sort of like changes the game when we start adding these things together. So before we even write out the terms in number 8, the sequence of 3n cubed over n cubed plus n, would that converge or diverge? Diverge? Okay. Does anyone think it would converge? So let's just see, how do we test? What do we have to compute? The limit as n approaches infinity on 3n cubed over n cubed plus n. So how do we compute that limit? Simplify it in what way? Okay, we could factor an n out of the bottom. Yeah. And then we could reduce from the top. Yeah. There's an easier way to do these.
Take out the 3.
We can take out the 3, yeah, but we don't even need to do any of that. Remember this, in terms of n, this is a polynomial over a polynomial. So when we compute the limit at infinity on a rational function, it's equivalent to just looking at the leading term over the leading term, right? Because as n goes to infinity, we have down on the bottom especially, we have infinity cubed plus infinity. Just think about that as an extremely large number cubed plus the extremely large number. If I add 100 billion to the third power plus 100 billion, it's pretty much 100 billion to the third power, right? You can put that in your calculator to check, but I assure you. So this is approximately the same thing as just, well, I mean, it's really equal to, as long as we're talking about a limit at infinity, to just 3n cubed over n cubed. So I'll erase this and put an equal sign here. Which is just 3. So the sequence converges to 3. We can spend time writing out the terms to verify that, but we know for sure, based on the limit, the terms get closer and closer to 3. In fact, like the 5th term is like 2.88. So, you know, again, it's not saying that the 5 billionth term will be identical to 3. It's just saying the 5 billionth term will be super close to 3. Maybe it's 2.99952 or something. Okay, so converges sequence converges to 3. So I think we're all capable of computing these terms. I'm just going to write them out in numeric form. So this is a sub 1 is 3 over 2, which is 1.5. A sub 2 is 24 over 10, 2.4. I'll just list them out like this. I think A sub 3 is 2.7. A sub 4 is 2.82. And A sub 5 is 2.88. So I mean, maybe if we just went out to the first 5 terms, we would say, well, maybe that sequence converges to like 2.9. But we have a surefire way limits at infinity to compute what it actually converges to. Does that make sense? Does anyone have any questions on what we're doing? Why it works or any of that? So have you all heard of the Fibonacci sequence? Heard of that?
Yeah.
It's pretty like well known. So you might have heard it outside of the context of like a higher math class, but the idea it's based on this guy. That wasn't his actual name, but Italian guy was studying like reproduction habits of rabbits on an island, and sort of simplified the situation. But it says you got a pair of rabbits at the end of the first month, and those pair of rabbits at the end of the next month reproduce another pair of rabbits, and then the reproduction continues in that fashion. So a pair of rabbits takes a month to mature before they have another pair of babies on their own. After 10 months, how many rabbits would there be? So first month we have 1, second month we still have 1 pair. The third month now we have 2 pair, fourth month we have 3 pair, fifth month we have 5 pair. So how many rabbits in total would we have at the end of the 10th month? So I mean, if you've seen the Fibonacci sequence, then it's really intuitive. If you haven't, we've got to figure out, like, is there a sequence to this? Yeah, it's 1, 1, 2, 3, 5. What does that look like? Probably not going to come up with the explicit formula for that, but can we look at 5 and say, based on the previous term or terms, how could we come up with 5? The last 2 terms, right? If I take 3 plus 2, I get 5. So does that work? How do I get 3? It should be this thing plus this thing. Is that right? Yeah, 2 plus 1 is 3. How do I get 2? It should be 1 plus 1. So that's it, right? I can't go back 2 more terms after that. So recursively, and we'll write the pairs down here in a minute, but recursively, since the next term is built upon or based upon the 2 terms prior to it, we need basically 2 initial conditions. You need the first and the second terms. We would say that A sub n is defined as how? Yeah, A sub n minus 1 plus A sub n minus 2. Or we could just, keep working with the pattern that we have. So at the end of the, we'll come down here, at the end of the 6th month, how many rabbits, or how many pairs do we have? 8? Do y'all agree with that? We just add up the 2 previous ones, 5 plus 3. Or you can think about it as a sub 6 is a sub 5 plus a sub 4. So we have 8 pairs. At the end of the 7th month, how many pairs do we have? 13. 8 plus 5. 8th month. How many pairs? 8, yeah, 21, 18, or sorry, 8 plus 13. 21. 9th month. 34. And the 10th month. 55. So at the end of the 10th month, we have 55 pairs, which means we have 110 rabbits. There is an explicit formula for this. I'm not going to talk about it, but the thing with the Fibonacci numbers, though, if you look at more and more of them, and you take the ratio of, like the 10th term over the 9th term, and the higher you go, like if I took the ratio of the, 1,000th term over the 999th term, they approach a specific number, and you might have seen like the golden ratio or the golden mean. You might have heard about that. So that's one of the ways which you can kind of show that ratio or that mean is by subsequent quotients of Fibonacci numbers. But anyhow, so I think we'll pause, take a break before we actually start talking about series. But remember, the difference between sequences and series, a sequence is just a list of numbers. A series is, we're going to take that list of numbers and add them all together. Okay, so then we're sort of shifting gears now. 8.1 includes both sequences and series, and so we'll talk about an infinite series. The sum from k equals 1 to n. And again, with the summation, the index k is incremented by counting numbers, 1, 2, 3, 4, 5. So this sum is really a sub 1 plus a sub 2 plus a sub 3, etc., 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 all the way to n. And I mean, I guess technically that's not an infinite series, because this would have to go from 1 to infinity. Otherwise, it would be a finite sum. So notice a series is, we can look at a series like it's a sequence, but we're adding each one of those terms. Our sequences previously was a sub 1, a sub 2, a sub 3. Now we're adding those terms. So you get this, a minor adjustment of adding the terms gives you this like huge shift in how you have to handle these things. So we're going to consider, let's just start off by considering the sum from k equals 1 to infinity, 1 over 2 to the k. And so what we're after is, if we have a particular series that's given to us, does it converge or does it diverge? So that's really kind of the main idea of most of Chapter 10, and coming up with various kinds of tests for particular types of series. Okay, so maybe we can write this out or make it formal later, but would it suffice for me to just say, all right, well, what's the limit of the 1 over 2 to the k as k approaches infinity? Would that tell me whether that converges or diverges?
No, it does.
No, how come?
Because it happens.
Because you're adding each term. It's not just a list of terms, right? So the difference with what we were looking at is it was sufficient enough to just compute the limit as n approaches infinity on a list of numbers, because what that limit at infinity for a sequence told us was, the term way out there, the tail, those terms are approaching 3, or they're approaching 0, or whatever it was, right? So we're not doing anything but listing those numbers out, and those numbers are getting closer to 3 or to 0, right? But when we start adding those numbers up, the limit on this term here, the limit as k approaches infinity on 1 over 2 to the k would be what? Would be 0. But what does that actually tell me in the sense of I'm summing all those things up?
Eventually, you're going to start adding close to 0.
Yeah, exactly. All this tells me is that the tail, the far end of that, the tail terms at the end, we'll say, the quote-unquote end, approach 0. Terms at the end approach 0. That is, in the sense of a series, eventually you're adding 0 plus 0 plus 0. Okay. Is everyone clear on that? You have to make that firm distinction now. It's super important. So when we compute the limit as k approaches infinity on 1 over 2 to the k, 1 over 2 to the k is just the kth term. And so what we're saying is the kth term approaches 0. It doesn't say anything about us summing up all of those things before it. But it does say that if we list all these numbers out, like 1 over 2, 1 over 4, comma, whatever, eventually that these things will be close to 0. That's all that's saying, is if we're looking at the list of numbers, that's all that limit tells us. Is everyone okay with that?
So, how do you know where the cutoff is to stop adding it?
So the fact of the matter is we're adding infinitely many of them.
Yeah.
So we kind of need to talk about that. It doesn't really show up till later, but the idea is that it's in order for something that I'm adding subsequent terms up, in order for it to converge, it is necessary that the terms eventually approach 0, but it's not sufficient to guarantee convergence. So what that means is, just because the tail, the term way out here, just because those terms get approach 0, doesn't guarantee convergence. Right? This is, what they say is that the terms approaching zero is a necessary condition for convergence, but it's not sufficient to guarantee convergence. So necessary condition versus a sufficient condition are two totally different things. Sounds weird. But
Yeah, that does sound weird.
It's
Seems like you're always gonna have some number that you're gonna end up with, you know, and then you're gonna stop adding to it.
It's kind of like that example of when we integrated 1 over x from 1 to infinity versus 1 over x squared from 1 to infinity in 8-9. The 1 over x integral diverged, but the 1 over x squared integral converged. So it has to do with like the speed of it. So I don't know, just this as a side note, necessary. A necessary condition is, I don't know if I wrote this down. A necessary condition is like, I don't know, a conditional statement is like, if this, then this, right? So a necessary condition is something that says, like, without, I don't know, we'll make it generic and write a specific example. Without a condition, you don't have a conclusion. So I guess a real life example of a necessary condition is, for example, it is necessary to have gas in your car. To go somewhere, I guess. It's necessary that you have gasoline in your car to go, but is that a sufficient condition so that you can go? No, just because you have gas in your car doesn't mean it's going to go, right? Multiple issues, I don't know, batteries, whatever, could, right? So, but it's necessary that you do have gas. Sufficient. Sufficient condition is basically saying if you have a statement, well, if you have a statement, how do I want to say this? We'll just say we used P and Q. We'll just say P guarantees Q. So see, sufficient is a stronger statement than a necessary statement. So like an example of sufficient condition is rain is sufficient for the ground to be wet. But is it necessary? Is it for the ground to be wet, is it necessary that it rains? No. Somebody could dump out their water bottle, whatever, right? So sufficient is a stronger statement. So when we say it's in order for a series to converge, that it's necessary the terms approach zero, it doesn't guarantee convergence. Just in the same way that if I say it's sufficient for your car to go that you have gas, or sorry, it's necessary for your car to go to have gas, it doesn't guarantee your car is going to go. Does that make sense? So that's kind of the difference with a necessary versus a sufficient condition. So you can't answer the question, does a series converge, just by looking at the limit on the terms themselves. So then the idea is like, can we take this infinite series and look at it through the lens of a sequence? So that's what we're gonna do. We're gonna take the infinite series and view it through the lens of a sequence. Specifically, oh man, it's all together. Specifically a finite sequence, and then we modify that finiteness. So if we're going to look at a series in terms of a sequence, it doesn't make sense to look at just the terms, because we're adding the terms. So what it makes sense to look at is a sequence of what we call partial sums. That we just call capital S sub n. So capital S for sum, n is some finite number. And then the way we sort of configure that is we say, all right, well, let's focus for a moment on the sum from k equals 1 to n on 1 over 2 to the k. So that finite series, and here I'll highlight this n here. This n here is equal to S sub n, our nth partial sum. So I know it seems a bit abstract, but let's go ahead and look at it like explicitly written out for some of these terms. So let's list the terms of 1 over 2 to the k. So again, we're just listing out each term, keeping in mind that that summation indicates that we have to sum those terms. So the first term when k equals 1 would be what? 1 over 2 to the first. The second term would be 1 over 2 to the second, which is 1/4. The third term, 1 over 2 cubed. Fourth term, 1 over 2 to the fourth. And maybe we'll look at the fifth term. What's the fifth term? 2 to the sixth is 32 times 2 is 60. Okay, so on and so forth. So we've already said, hey, just because these terms approach 0, that doesn't mean that this thing is going to converge. But if we look at a sequence, in particular a sequence of the partial sums, then maybe that can give us some insight, because at least with the sequence of partial sums, we're more closely related to the series itself, because we are actually adding things together. So let's, our terms for this sequence are 1/2, 1/4, 1/8, 1/16, etc. You have to add those. For this thing here. So this sum is 1/2 plus 1/4 plus 1/8. It's a 16th and so forth. But as we'll see, what we've written out here with this sum up to n, what we've written out here is the sequence of partial sums, particularly the nth partial sum is what we have expressed when we write this out like this. So the partial sums the first partial sum is just the first term, 1/2. So if we just add one term in that series, you just get a half. The second partial sum is 1/2 plus 1/4. What's the third partial sum? 1/2 plus 1/4 plus 1/8. Does everybody see how the partial sum thing works? What's the fourth partial sum? Well, it's just the sum of the first 4 terms. Let's go up to the fifth one, I suppose. So the fifth partial sum is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Add up the first 5 terms. What's the nth partial sum then? How many terms do we add up? Yeah, n of them. It's a bit more abstract, but we already have this written out. That's 1/2 plus 1/4 plus 1/8 plus 1/16. You know, we could keep going on in this pattern, or we could just say plus dot 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 1/2 to the nth power. So we're adding up the first n terms for the nth partial sum. And notice we've already written that out, right? That nth partial sum is this sum right here, up to n. So this is, when we write out the sum from k equals 1 to n of 1/2 to the k, we can express that as the nth partial sum, s sub n. Is everyone okay with that? So since the partial sums, we should write these out. This is up to 5. So we'll do here, here, here. Let's get an idea of these values. So that's our 1/2. That's going to be 3/4. That's gonna be 7/8. That's gonna be 15/16. And this is gonna be 31/32. So when we look at the sequence of partial sums, we already have the sums built into each one of those terms, right? This was the first term, first plus the second, first plus the second plus the third, et cetera, et cetera. So at least with the list of these numbers here, we already have a sum built in, which is what we're after anyways, because we're dealing with a series, a sum of those numbers. But again, remember, all we're summing is these terms here, 1/2, 1/4, 1/8, 1/16, 1/32. When we sum those, we get 1/2, 3/4, 7/8, 15/16. Okay. So now that we have this, our sequence of partial sums are those numbers: 1/2, 3/4, 7/8, 15/16, 31/32, 63/64. We didn't write that one down, but on and on we could go. So since those terms in that sequence there actually represent portions of the sum that we're trying to answer a question about, then we can say, all right, I've taken a series, I've now looked at partial sums, and now I'm looking at that series as a sequence of partial sums. So we can ask the question, with the sequence of partial sums, how would we use this to know or find out if the infinite series, okay, from 1 to infinity of 1/2k, converges or diverges? Remember, these things we have here in purple represent sums. Right. So we can say, does the sequence of partial sums, which are just portions of that original sum, right? We can see, like, as we extend those out, as we go out to infinity, does it actually converge to a specific number, right? So we'll see this in a theorem or a definition. I forget which one it is. But the idea is that I can take this infinite sum of 1/2 to the k. And remember what that actually means, kind of in the sense of how we looked at our indefinite integrals, that this sum here actually means the limit as n approaches infinity. The sum of k equals 1 to n of 1/2 to the k. Do y'all agree with that? But in terms of the sequence of partial sums, we've already noted that the sum from k equal 1 to n of 1/2 to the k is just another way to write the nth partial sum. So now we can say, all right, well, if I want to know what the sum of that infinite series is, I've got to know how to express my nth partial sum in terms of n, explicitly in terms of n. And then to compute the sum of that series, all I need to do is look at the limit on the sequence of partial sums. Does that make sense? So in fact, this statement that we've written here, the sum of this series out to infinity, is the limit on the nth partial sum, the sequence of nth partial sums. That's true for any series. The problem with most series that we encounter is it's not conducive, nor is it doable, nor is it easy to write out an explicit formula for the nth partial sum. Here we can. So this is virtually our answer. Our answer is that the infinite sum is equivalent to looking at the limit on the nth partial sum. So we'll say this in words, the sum of an infinite series is equal to the limit as n approaches infinity of the nth partial sum, the sequence of n, we'll say the sequence of partial sums. Which is this. But again, that the explicit formula for S sub n is not always, you can't always find that. Okay, so this right here tells us that we need an explicit formula for S sub n. So can we find an explicit formula for that sequence that we wrote out? 1/2, 3/4, 7/8. So it might be helpful to remember that this was your first partial sum, this was your second, this was your third, and so forth. That way we can relate our indices 1, 2, 3, 4 to the actual construction of the number 1/2, 3/4, 7/8, etc. So just take a minute and look at that 1/2, 3/4, 7/8, 15/16 when n equals 1, 2, 3, 4 respectively, and see, is there a pattern that we can explicitly write out to get, when I say n equals 5, the formula should spit out 31/32. When I say n equals 2, the formula should spit out 3/4. So hopefully you can see the denominators, we can start with the denominators because it's straightforward, right? It's 1 to 1. The denominator here is 2 to the first. The denominator for S sub 2 is 2 to the second, right? So what is the numerator in relation to the denominator? It's just 1 less. So we have 2 to the n on the bottom and 2 to the n minus 1 on top. This right here, it's secretly multiplied by 1. Not that we need that here, but this is, if we look at it this way, it's a little bit more conducive to when we look at other ones, as we'll point out. But so 2 to the n minus 1 over 2 to the n gives us that particular nth partial sum, right? If I said, what's the sixth partial sum, then I have 2 to the 6 on bottom, which is 64, and 64 minus 1, which is 63. So I get 63 over 64. So that's the bulk of the issue there. Can we find an explicit formula for S sub n? If we can, then all we need to do is go back to this statement here that we have the star and say the infinite sum is actually just the limit as n approaches infinity on that formula for S sub n. So we're going to go back here and say that this series is equal to the limit on our partial sum, which we now know to be the above. Because now these terms, 2 to the n minus 1 over 2 to the n, those represent future sums in that series. The 1 over 2 to the k didn't represent a sum in any way, so when we looked at the limit on that, only thing it told us is that, yeah, eventually the terms themselves actually approach 0. That may or may not mean that this series converges. So what's the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n? 1. And again, we look at that in a similar way we look at polynomials.
Infinity minus 1.
Since n is going to infinity, all we have to do is look at the leading term over the leading term. The minus 1 up top is insignificant out towards infinity. So, let's just write that as sort of an intermediate step. That's equivalent to the limit as n approaches infinity on 2 to the n over 2 to the n, which is equal to 1. So what that means is that our sum from 1 to infinity, the infinite sum of 1 over 2 to the k, is actually approaching 1. So the way we say that, though, is thus sum from k equals 1 to infinity of 1 over 2 to the k. We say that's equal to 1. But again, we've got this infinity, so we've got to be thinking in terms of limits. It's not saying that if I add, I don't know, whatever the biggest number you can think of, if I add that many number of terms, that the sum will be identical to 1. It's just saying that that sum gets closer to 1. If we could add out to infinity, then it would be 1. But you can't do that. So it's kind of like a limiting thing. And so this right here, I know that was a lot of work. This right here is I'm just going to take from your textbook. So we start off with this 1 by 1 square. Now that we know the sum is actually equal to 1, and then we're going to look at the nth partial. Let's see if I can get that in there larger. We're going to look at the nth partial sums. So we have the first, which was a half, the second, which was 3/4. And you see, as we keep adding more and more terms, the thing never breaks out of the boundary of a 1 or 1 by 1. So that's sort of our visual justification, if you will. I'm going to put that there instead. Keep that. Try that again. That's a long page.
Because, like,
Yeah.
so what ends up
So, I know that was a lot to take in, but hopefully it sort of made sense in the way we pieced it together. But the idea is that if you can come up with an explicit formula for the nth partial sum, sorry, that's kind of what this definition is spelling out. The limit on the nth partial sum is equivalent to the sum of the series. So that we see that specifically here with that statement. And, you know, I guess they don't really have the caveat here, but the caveat is you can't always find that explicit formula for the S of n. But anyway, since we discussed that in that example, this is where you'll find the actual definition. Did anyone have any questions on this example? So then maybe you're already thinking like, well, if you can't come up with an explicit formula for n, how do you know if the thing converges or diverges? And really the answer is there's, I don't know, 5, 6, 8 different tests we have to utilize. So yeah, you have to remember all of the tests and what they say. But it's not a trivial thing. And in fact, a lot of those tests will merely tell us if it converges or diverges. They will not tell us what they converge to if they converge. So then that's another problem altogether. So it's definitely not a trivial thing to talk about these things. But we're talking about these things because eventually we're going to say, well, if this series converges to 1, maybe if I throw a function in there, I can get it to converge to 1 times that function. And so maybe 1 over 2 to the k actually represents a function that I've been working with all the way up until this point. Maybe it doesn't. But that's for us to determine later. Another type of example is these repeated fractions. So like if we take 0.3 plus 0.03 plus 0.003, et cetera, we can look at that as a series as well. So the first 5 partial sums, this would be plus 0.00003. So what's the first partial sum of this series? Yeah, 0.3. The first partial sum is always just the first term. The second partial sum is the sum of the first 2 terms, 0.3 plus 0.03, which is 0.33, and so forth. Third partial sum sum of the first 3 terms, which is 0.333, and so forth. So we could say that, right? Because this right here is your third partial sum. And to get the fourth partial sum, we just take this here, which is s sub 3, and then we add the next term. Our next term is a sub 4. So here's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. Everybody okay with that? We'll see how this unfolds. And the fifth partial sum is the fourth partial sum plus the fifth term. All right. 1, 2, 3, 4. Yep. So make a conjecture for the value of the infinite series. What do you think it is? 1/3, right? Just 0.3 repeating. How do you represent 0.3 repeating as 1/3? Like maybe that one's trivial, maybe it's not. But in general, how do you take a repeating fraction? There's more of a, I guess, a series approach, which we'll talk about later, but there's also an algebraic approach. So like, let's say we didn't know that 0.3 repeating was 1/3. What we do is we say let, I don't know, let u or w, x, whatever, let u equal to, I don't know how many we want to show, but whatever, 0.33 repeating. If that's our u, then we can say, all right, well, if u is this, then 10 times u is 3.3 repeating. And so what happens when we take 10u minus u? What do we get?
3.
Does everybody see that? If I take 0.3 repeating and subtract off the 0.3 repeating, I just get 3. So I actually have 9u is equal to 3, which means u is equal to 3/9 or 1/3. So our u, which was 0.3 repeating, is actually 1/3. That's how you know it's 1/3. If it's something where you have like every 2 repeating, like if it's, let's say it's 0.3434 repeating, then you still let that equal to u, but you want to look at 100 times u. So you have 34 with the 3/4 repeating. So when you subtract those, this u here gets rid of that repeating portion. So then you would have 100u minus 1. So you'd have 99u is 34. So 34/99 is 0.343434. So that's sort of like an aside kind of thing. But anyhow, that's the algebraic way to represent repeated fractions as a rational number. So that's our conjecture. I mean, that's what the partial sums show us. That we're just adding 3 in the tenths, hundreds, thousandths, etc. places every time we look at a different partial sum. The other way we can think about this is we could try to represent 0.3 plus 0.03 plus 0.003, etc. as a sum itself. So, the other way we could technically think about this is, can we take this sum here and write it out as some sort of sum? Like, what is that equal to as a sum explicitly? Like, what is the closed form of that sum? Or the finite version of that sum, if you will. So, I don't know, maybe it's conducive to think about this as 3/10. This is 3/100, and so forth. So how will we represent that as a sum?
3/10 to the
3/10 to the
n.
n? Okay, so could we represent this as 3/10? Which one's to the n?
10.
Just the 10?
Just the 10.
Could we represent that as 3 over 10 to the nth power?
Yeah.
We'd start at where? N would start at 1, and then we would just go off to infinity to get that, right? So the first term is 3 over 10 to the first, plus 3 over 10 to the second, plus 3 over 10 to the third. So the 3 is really insignificant, right? We could factor the 3 out of every single term. Or, you know, if you want to see that, as we might see that in the future. That's 1/10 to the n, and we have all of that times 3. Or what we can do that sometimes is done. What if we said, well, I have this sum. I want that to start at 0. I don't want it to start at n equal 1. How could we rewrite this sum so that we can start out with 0 or at 0 instead? Yeah. We just add 1 to this right here. So in the summation, like what you do, in the expression you're summing, rather, what you do to the index, you have to do the opposite of the index that's attached to the summation. So we added 1. We added 1 here, so we subtracted 1 from here to give us that. They're exactly the same representation. Well, sorry, different representation, same sum. Okay, so like we haven't talked about it, but I think it's, if you can look at it like that, then we can look at this as a series that we're actually going to spend time with in 10.3. Okay, so the example 11, do y'all have any questions? So again, if we looked at this infinite sum and say the terms of the sum are going to 0, right? Each term is getting subsequently smaller. In this particular instance, and in the particular example we had 1 over 2 to the k, we did see that, yeah, the terms approached 0, but the sum also converged, right? But in general, just because 1 over 10 to the n approaches 0, it doesn't guarantee that your sum will converge. So you have to like get that stuck in your head, because it's a huge pitfall that people fall into. They say, well, I'm just going to compute the limit on this term right here. I don't know what happened there. Since it goes to 0, then that means the sum of all that stuff has to converge. It is absolutely false. So consider, we'll revisit this, but consider the sum of 1 over k from 1 to infinity. The limit as k approaches infinity of 1 over k is equal to 0, means eventually you're adding up zeros, right? But the series diverges. I know I'm probably getting ahead of myself by talking about this stuff, but I really do think I see people just struggling with this concept or using the wrong kind of reasoning to say something converges. So just want to mention that like right out the gate. That's our classic counterexample. The limit of the terms going to 0 is necessary for a series to converge, like the last two examples. But here's an example of when it's not sufficient. Even though the limit of the terms 0 the series, or the series itself still diverges. So that's not a sufficient condition that this limit be 0. Okay, so that's just I'll probably write that down again and reference that again. What if the limit of the terms didn't go to 0? Would that guarantee that it diverges?
Yes.
So I'll let you think about that. We will talk about that eventually, but. Okay, so that was our definition. So consider 2 times k over k plus 7 root k. Find the first 4 partial sums, and then make a conjecture about the value of the infinite series. So if you're using a calculator to find these things, I'm really okay with that. I think for a lot of your homework, they have you write out like partial sums, and it's tedious, it's time consuming. So if you're using some sort of device to do so, I don't really care. Even if something like this showed up on the exam. First 4 terms of the sequence of partial sums. So actually, before we find the sequence of partial sums, we need to find what this series is composed of. Like, what are the terms of this series? So actually, let me write it this way. We're actually only after the first 4, sorry. We're after the first 4. So when we write this sum out from 1 to 4, that will be the same thing as the 4th partial sum. So really all that means is we need the first 4 terms of that series, and then we need to add them together. So I'll do this here. The first term of our series when k equals 1, we have 2 times 1 over 1 plus 7 root 1. So we have there just as 2 over 8. Which is 1 over 4. Okay, since we're running a little behind, I'm just going to write these out. A sub 2 is about 0.336. The third term of the series is 0.397. That's a 0. And the fourth is, I don't know, 4 over 9. You can actually compute the square roots of some of those. Okay, so we have the first 4 terms, then we can get the first 4 partial sums. So again, first partial sum is the first term. Second partial sum would be what?
The second and first.
Yeah. We have the first term plus the second term. Which let's give us 5861. 0.5861. Okay. S sub 3 is 1/4 plus 0.336 plus 0.397. Then it gives us 0.9829 as the third partial sum. And the fourth partial sum, we'll shorthand this again, 9829 plus our 4/9, which gives us 1.4273. So this is one of the examples where it would be really, really hard to come up with an explicit formula for the interpartial sum. Because some of them involve radicals or irrational numbers, and some of them don't. So the best we can do is say, all right, well, let's just look at those individual sums and put that together as the sequence of partial sums, 1/4, 0.58, 0.98, 1.4. And if we kept on in this direction, S sub 5, S sub 6, S sub 7, what would we conclude? Like, just based on on what we've done, does that particular series converge or does it diverge? It diverges because we see that the sums keep getting larger and larger. So maybe we can write that down next time, or I'll put it in your notes now, but I think that's it for us. Do y'all have any questions before you leave? All right, see you Thursday. Oh yeah. Do y'all want the test back? Yeah, sorry, I totally forgot. Okay, we'll continue this one next time.